All right, so today will be a review class. I'm going to go over primarily practice exam 2. And first of all, I think Proctor track is not available. It's still not available. Let me check. Right. So because our second exam is next week, and so we probably won't be able to use Proctor track this time. And so what I'm gonna do is we're just gonna take the exam in our class time. So next Tuesday, you will still come to join the class using Teams the same way, and I'll just proctor the exam. So you just need to turn on your camera, and I will just proctor the exam this way. Okay. Any question? Okay, so the second exam will be this coming Tuesday, okay, November 3rd. All right, so let me go over the practice exam here. Okay. All right, so exam 2 will cover the following topics: indirect proof, proof by cases, mathematical induction, and set theory. We will have set notation like belong to or a subset, set operations, intersection, union, and all those. Venn diagram, and the proof problem for chapter 5 will be how to prove a set is a subset of another or prove two sets are equal. Again, I notice in the grading, some students still have trouble with that. So today I would focus on that and give you, well, kind of go over the practicing. And if I have time, maybe go over the homework problems. Okay, and the last type will be counting problems using addition rule, multiplication rule, or permutation and combination. All right, so I also listed the sections in there and which week we covered these topics. So if you want to go back to watch the videos again, you can go say you want to go over indirect proof again, go over the examples again. You can go back to week 6 and the videos are posted there. So the class videos. Okay, so now let's look at the first question. I guess, well, I think it was it Marley? I think on your when you send your homework to me for me to check for this question, I forgot to list another case, and maybe that's why you didn't do the third case. Actually, usually we do 3 cases for this one. All right, so this is an example of proof by cases. So as I explained before, why do we have to do cases? Why cannot we just do one case? Because one case it's not going to work. So for example, when we try to show something is divisible by 3, just like 6 is divisible by 3, the way we show it is trying to factor 6, factor 3 out of 6. So you can show, okay, well, 3 goes into 6 2 times, which is an integer. So that's the idea behind the proof. So the same thing, without having a number, we have expression. We can still do factoring. We're learning algebra, and we want to factor. So we want to factor a 3 out of here. Well, when you look at it, it's impossible. There's no 3 here. So that's why we have to do cases. But like I said, if you want to go back to watch the detail of the proof by cases, because I don't think I have time to start from the beginning again. So like I said, you can go back if you want to look at the proof by cases. It's under week 7, and you can go back and try to go over those different cases, different examples. Okay, so we could do 2 cases for any integers. So remember, when we are doing cases, we're focusing on the integer n, because without knowing what kind of integer n is, we cannot factor out of 3. So that's why I was thinking, well, we can maybe discuss different category, different cases for n. Now, of course, we could do even or odd, but Unfortunately, if you do even or odd, let's say even number can be described as 2k. Odd number can be described as 2k plus 1. But after you plug 2k in here, you're still not going to be able to factor out a 3. So we can do a quick check here. So I'm going to replace n with 2k in both for both n, and 2k cubed is 8k cubed plus 4k. You will be able to factor out a 2 or 4. You won't be able to factor out a 3. So that tells us, okay, well, if I only do 2 cases, even or odd, it's not going to work. So that doesn't work. So that's when I started thinking, well, maybe I should do 3 cases. 3 cases, which means this integer can be divided into categories of multiple of 3, multiple of 3 plus 1, or multiple of 3 plus 2. So remember, just like if I have a group of class students, I can divide it into any way I like. So for example, I can divide it into 2 groups by gender, female and male. I could divide it into 3 groups by maybe major. Maybe we have, English, math major, education major, and engineering major. So I can divide it into 3 groups. Well, so it's the same students, but I can divide it into different groups. So similarly, when we have integers, we know integers are, like 0, positive 1, negative 1, and positive 2, negative 2, positive 3, negative 3. But these integers can be divided into different groups. If I divide them only into 2 groups, that would be even or odd. But I can divide it into 3 groups. Where's my... Okay, so I could divide them into 3 groups, which are 3k, 3k plus 1, or 3k plus 2. Okay, because any integer, it's either any integer n, it's either multiple of 3, like numbers 3, 6, 9, 12, those numbers. But if they're not 3, 6, 9, 12, they will be like 1, 2, 3, 1, 4, 7, like those integers, 1, 4, 7. These will be multiples of 3 plus 1, because you can see when you divide 4 by 3, you get remainder 1. When you divide 7 by 3, you get remainder 1. So all of these numbers right here, I can always write them. For example, 4, I can write them as 3 times 1 plus 1. 7, I can write them as 3 times 2 plus 1. And 1 actually can be written as 3 times 0 plus 1. So all of these integers, there are infinite many, can be written in this format, 3k plus 1. And similarly, we have 2, 5, 8. These integers can be written as 3k plus 2. Okay, all right, so that's why usually after you do a few examples, practice problems, you probably will get idea. If you want to factor out 3 from that expression, when you do 2 cases, you're only going to get a 2 or 4. It's not going to get you a 3. So probably, 3, we have to do 3 cases. Okay, and the worst case, you tried 2 cases, it didn't work, and that's when you realize, okay, we got to try 3 cases. All right, so here I'm going to write down the proof. Most students did this right. So because I cannot prove it directly, I'm going to prove by cases. Since n is an integer, so we can divide n into 3 cases. N equals 3k, n equals 3k plus 1. There's a minor mistake in the, I guess, multiplication process. I forgot who made that mistake, but so for the first case, when we replace n with, when we replace n3k, we could distribute the exponent to each factor in the base because it's multiplication. So we could do 3 to the third, 27, k to the third, k third, plus 6k. But when you do the second case, after you when you plug in, we cannot just distribute the exponent anymore. Okay, so let me go ahead and replace it. So how do we work this out? By the way, it's not going to be 3 to the third, k to the third, and plus 1 to the third. This is incorrect. Okay, it's missing a lot of terms. The correct way to do it is you have to do, if you actually after the exam, next Thursday, I think we will talk about it. We will give you a formula to a direct formula. You may have memorized in your algebra class, but we will actually give you a formula for any exponent. So even fourth power, fifth power, there is a formula, but it's not going to be distributed. Okay, remember, when can you distribute the exponent? It has to be multiplication. If you have a plus, you cannot distribute the exponent anymore. Okay, so the way to do it is to do 3k plus 1 times 3k plus 1. If you have not memorized the formula, which usually not required, you don't have to memorize the formula, you have to do 3 copies. So you multiply 3 copies of 3k plus 1. Let me bring that down there. And to do that, you will have to multiply, you got to use FOIL to multiply these two out to get, I'm going to go ahead just write down the answer after you do FOIL. So that's what we're going to get. And multiply the third copy of 3k plus 1. Okay, let me go ahead and multiply these out. So you get a 6k plus 2. Now, again, here you just distribute. We can't use FOIL, just keep distributing. So you will get 9 times, I'm going to go ahead and just write down the answer to save time. So you should distribute like 3 times. So distribute 9k squared to 3k, 9k squared to 1. And then 6k times 3k, 6k times 1. And then 1 times 3k, 1 times 1. So after you do all that and then combine like terms, you should get 27k cubed plus 27k squared and plus 9k and plus 1. Okay, so after you do that, and there's also plus 6k plus 2. Let me move it here. And then we can combine these k terms and the constants. We should get 27k third plus 27k squared. And this 9 plus 6, that gives us 15k, and that 1 plus 3 gives us 3. Okay. By the way, for the case 1, I didn't finish. I just wanted to point this out, okay, because I did see once in the past some student did make that mistake, so they thought it was just going to be 27k cubed plus 1, but that's not the correct formula. So in fact, we still have to do one more step to show, because our goal is to show this expression is divisible by 3. In other words, we can factor a 3 out of here. Looking at the original expression, we couldn't. But after we know more about this n, so we know more detail about n. So if n is a multiple of 3, after we plug it in, you can see we are able to factor 3 out. Okay, by the way, we don't need to factor out the greatest. We just need to prove it's divisible by 3. All we have to do is to factor out a 3. Okay, and when you get here, you can say, well, it's divisible by 3. Let me just use symbols. So therefore, 3 divides m third plus 2m. Okay, so that would be the first case. For the second case, after you plug in, you do all that algebra work, and you can see you're still going to be able to factor out a 3. That's 9k third plus 9k squared plus 5k plus 1. And same thing, you can see we are able to factor out a 3 from here. So therefore, 3 goes in there. For the third case, I'm going to be a little quicker because it's going to be exactly the same thing. I did see some students try to do indirect proof for this one, said this is not divisible by 3, and it's probably not going to work because if you want to do indirect proof, you have to find a contradiction, but it's going to be very difficult to find a contradiction this way. Okay, so this is still direct proof, but we just have to do 3 cases. Okay, so I'm going to go ahead. All right, so it's the same thing. How do we multiply this out? You will have to multiply 3 copies of this. So I'm going to just go ahead and write down the answer for this. 18k squared. Like I said, there is a formula for this. I'm trying to apply the formula here. So 12k squared. Oh, did I have it? Okay, 12k and plus 8. Okay, so later after the first exam next Thursday, I will give you this formula. and distribute 3 to those, 6k plus 4. Okay, now we combine like terms. So by the way, when you if right now you don't know the formula, all you have to do is just take 3 copies, multiply 3 copies. So plus 18k squared plus combine these two, 18k, and combine these two plus 12. Okay, so now we can still factor out the 3 from this expression. Okay, all right, any question about this example? Okay, so, and then you say, therefore, 3 divides n third plus 2n. As you can see, for each case, it doesn't matter whether n is a multiple of 3 or multiple of 3 plus 1 or multiple of 3 plus 2. I can always show 3 goes in there, goes into that expression. Okay, so that's the first one. Now, the second one, yes, go ahead.
Is that how it's going to be on the exam? Like, is it going to be a problem similar to that?
Yes, it will be. So you will have to do cases, but it could be 2 cases, it could be 3 cases. I don't think I will ask you to do 4 cases. Okay. Yeah, it's going to be similar. Other questions? Okay, no problem. Other questions? Okay. So again, each problem has like, I was trying to test you whether you know this technique to prove by cases. So it just in like in real life, sometimes when you try to solve a problem, real life problem, you may not be able to just do it in one way. You may have to do it for some cases you have to do this way. For some cases you have to do that way. Even you deal with the students, maybe you for really talented students, you might have to, give them challenging problems. And for the other case, maybe a little slow students, you have to give them, they have special tutors. And so it's just kind of like things like that. So the same thing, we won't be able to just deal with n just the same way. But after we divide it into cases, we are able to tackle the problem, case by case. Okay, now let's look at the second. Yes, go ahead.
Sorry, I have one more question about that.
Okay.
So you tell based on the exponent how many cases you need. So like that's n to the third. So that means 3 cases.
No, not the exponent. It's usually by this number. If you think we need to, if you want to prove it's divisible by 3, you need to be able to factor out of 3, right? And if you only do 2 cases, look what I tried. I can only get 2 or 4 or 8. It's not possible to get a 3 out, right? Because 2 cases only going to give you 2k. The expression will look like 2k or 2k plus 1. So either way, you're not going to be able to get a 3 there, because when you take, it doesn't matter what the exponent is. Even if it's squared, you're going to get a 4. So if it's squared, you're going to get a 4, right? If it's third, you're going to get 8. If it's fourth, you're going to get 16. So it's impossible to get a 3 out of there. But if I do 3 cases, look, where did that 3 come from? Because when you do 3 cases, it automatically has a 3 here and 3 here and a 3 here. Although it's not a 3 here or there, somehow after you combine like terms, you will. So for example, I got 1 here, but I got a 2 here. After I combine, then I was able to get a 3, right? So the same thing. I got 8 here. It's not a multiple 3, but there was a 4 here. After I combine, then I got a 12, which is still multiple 3. Okay, so usually it depends on the number here. Okay, but like I said, normally I would you would get this kind of idea. Okay, well, divisible by 3 probably should be 3 cases. So you can try 3 cases. If it works, great. If it doesn't work, maybe you have to try, add more cases or something else or some other ways. But yes, that's what I would guess. That would be my first try. So if it's divisible by 2, I would try 2 cases. If it's divisible by 3, I would try 3 cases. Because 3 cases will give me that 3. Does it make sense, Marley?
Yes, that makes more sense. Thank you.
Okay, so I can kind of highlight this number right here. So this 3 we eventually contribute to that factor 3 there. So the same, that 3 there somehow will contribute to that multiple 3 there. Other questions? Okay, so let's look at the next example. So again, when you take the exam, I may just give you 2 cases, okay? So if it's divisible by 4, do you think I have to do 4 cases? Not necessary, because I would try. So yeah, let me go ahead and just explain a little bit further. So if I have divisible by 2, most likely you do 2 cases. But if I have divisible by 4, do I have to do 4 cases in order to get a 4, to do 4k plus 1, 4k plus 2, 4k plus 3, and 4k? Maybe not. Maybe 2 cases will work. Why? Because look, when you have 2 cases, this 2 actually will give you multiple of 4, right? You see that? See 8 and 4 will be a multiple of 4. So if it's divisible by 4, I will still try 2 cases. It works. If it doesn't work, I try 4 cases. Okay. All right. Now let's look at. Oops, shouldn't do that. So let me look at the next case. Next example will be the indirect proof. So we have I think 3 problems. So the second one, the third one, and the fourth one, they're all indirect proof. The second one, I think a lot of students confuse this one with the fourth one, right? Because well, they're kind of similar, to show a radical number is irrational. But the second one is actually easier than the fourth one. Okay, so in direct proof, I wrote down the steps here. By the way, this PowerPoint slides will be posted on Blackboard. So maybe you can, I also put the steps there to kind of put everything together, summarize everything, so you don't have to go back to search in the past notes, and it's everything will be in here. Okay, so how do we do indirect proof? First step, you have to assume or suppose to the contrary, the negation is true. So whatever that conclusion is, this is the conclusion. And you gotta do negation, which was discussed during the first, first week of our class. So we write on the proof. I think everybody knows that. Again, the reason is it's impossible to prove something is irrational directly, because if you want to do that, you have to prove square root of a cannot be written as a fraction. And there are infinite many fractions. You're not going to be able to check every single fraction we have to verify it's not going to be square root of a. Plus here, we don't even know what a is. So suppose that to the contrary, well, sometimes if you don't want to write to the contrary, that's fine. Okay. Square root of a is rational. And rational means fraction. So which means then we can write a, let square root of a be. By the way, one student, I forgot who, used the a over b. That's what we usually pick, a over b, right? But I already have a here. You can't use a again, because when you have a fraction, it's most likely it's not going to be a over b, right? So you got to pick different letters to represent that. So b and c are both integers, and the c is not equal to, I guess maybe b and the c is not equal to 0. Okay, because if it's a rational, which means it's a fraction, so I should be able to pick a fraction. So let square root of a equal to b over c. Now the next step, again, whenever we do indirect proof, the most important step is step 2, to find a contradiction. How do we find a contradiction? Most of the time, when you look at this, you don't see any contradiction. So we got to do some algebra work, like simplify it to make it easier to analyze. So what we usually do when we see square root, it's not very easy to analyze the expression. So we are going to square both sides, because square cancels square root. So there are what we call inverse operations. So you are going to end up with just the a. On the right hand side, we have b squared over c squared. Now previously, for number 4, we do have to continue to get rid of fractions. When we do this one, I'll show you in a second. So I have to multiply both sides by c squared. That's what most students did in the grading I saw. But in this case, when you get here, so every step you get, you take a look, see if you can find a contradiction. Actually, there's no need to get rid of fractions here. So I know a lot of students did this, a times c squared equals b squared. But that's not necessary here, because when I look at the expression I got here, I already see a contradiction. Okay, so remember when you use indirect proof, as long as you can get as long as you see a contradiction, that's where you can stop. So when I look at this, well, the hypothesis tells us A is irrational. A, this letter A, variable A, should be an irrational number, but look at B squared over C squared. That tells us it's rational because it's a fraction. Fraction means rational. Well, I guess maybe let me erase of this. Okay, so it's not, you don't need to do get rid of the fractions here. So you would go ahead and just say, then A is rational. Well, if you ask them, I think everybody can see that, right? If you want to explain why, because since B squared over C squared is rational, is a fraction or is rational, is a fraction. Okay, but if that's obvious, maybe you don't have to explain that. But you can see if that that's rational, that means A equals that. That tells us A is rational, which is a contradiction. So it contradicts. Well, it contradicts what? The hypothesis. It contradicts the hypothesis of this conditional statement that, look, this. It says A is irrational. This is our hypothesis. So that A is irrational. If you put a contradiction there, it might probably be okay. But usually for beginners, I would recommend that you write down clearly so you know what the contradiction is very clearly. So these two statements are contradictory to each other, contrary to each other. Look, A is rational, A is irrational. I mean, it's impossible. When you have a number, it can only be one of those two cases. If it's rational, it cannot be irrational. If it's irrational, it cannot be rational, right? So the contradiction tells us our assumption is false. Okay, so you can go ahead and say, oops, therefore, square root of A is irrational. Okay. Again, if you don't write this down, it's not a big problem, but usually, so that's the end of the proof, QED. Some instructors are very strict about this. They want you to put a QED there. QED just means it's the end of the proof. Okay. I probably won't be too strict, but you can do that. Okay. So, any question about the second one? Okay, let's move on to the third one. Well, let me go ahead and look at the fourth one, and because the fourth one is kind of similar to the second, but it's more complicated than the second. We need to do more in order to see the contradiction. So suppose that first of all, following the steps, we assume that this is the conclusion. We want to negate this. So assume that this is rational. Similarly, if it's rational, then we can pick a fraction for this rational number, A over B. Now I can use A over B because there's no A here. A is an integer, B is an integer, and B is not equal to So, oh, by the way, in the second case, I didn't really need, notice that I did not even write down the greatest common factor of B and C is equal to 1 because that's not needed. After I square both sides, I already saw a contradiction. There's no need to continue to make sure that B over C is reduced anymore. But in this case, we do have to have this condition. And you will see for a second why we have to make sure this fraction we pick is a reduced fraction. Okay, so previously in the second example, whether this fraction is reduced or not, B over C, whether it's 3 over 4 or 6 over 8, it doesn't matter because after I squared, I still get a fraction, right? So it's not important whether this fraction is reduced or not. Either case, we get a contradiction. But over here, so we are going to square, not square anymore. So here uses a little bit of algebra. In order to get the third root, cube root, we got to take the third power. Because the third power and third root, they are inverse operations, and they sort of cancel each other. So we end up with 2 equals a cubed over b cubed. See, right here, I cannot get a contradiction because right here, a cubed over b cubed, that's a fraction. It's rational. 2 is also rational. I can write 2 as 2 over 1. So both are rational. Rational equals rational. There's no contradiction. But previously, because the problem gave us an extra condition, which tells us a is irrational. So immediately, this is irrational. We already have a contradiction here. So the left-hand side is irrational, but the right-hand side is rational. A rational number cannot be equal to irrational, right? So we have a contradiction immediately because a is irrational. But in our case, 2 is not irrational. So both sides are rational. Rational equals rational, no contradiction. So that's why we have to continue to simplify this further, see if we can find any contradiction. So what we're going to do is we get rid of the fractions. So we multiply both sides by b third. So times it by b third, times it by b third. So b third cancels b third. We end up with 2b third equals a third. Okay. Quite a few students said, okay, so a is even, but you need a little bit more explanation. How do you see a is even? From here, you can only tell a cubed is even because 2 times integer, right? If 2 times integer, then that tells us a cubed is even. So then a cubed is even. So if you said a is even, you really missed a little bit explanation. And so a is even. How did I know that? It's by number 3. I didn't prove number 3 yet, but I will go back to prove that. So look at number 3. What's number 3? Number 3 says if a third is even, then a is even. Okay, that's exactly what we have. A third is even, then a is even. Okay, so that's why I put number 3 there. And to ask you to prove it because you are going to need this when you do number 4. Okay, so since we already proved the number 3, I know I have not, but I will go back to prove that. So if a third is even, then a is even. Okay, now we can continue. If a is even, when we get here, we know a is even. There's still no contradiction. I think I saw one student just said, okay, by looking at this, I know a, b are both even. Well, most people cannot see why both A and B are even directly. I mean, why? It could be, it could only tell you A is even. It doesn't really tell us why B. B doesn't have to be even. B could be odd. So look, if I have 3 to the third times 2, if B is 3, I still get an even number. 3 to the third, 27, I get 54. I mean, that is even. So B doesn't have to be even from this expression. So we cannot tell whether B is even right here. So that's why we need to continue, because since we know A is even now, how about we let A be an even number, which is 2k. So we are going to plug it in here. Left-hand side, we keep it. Right-hand side, we replace A with 2k. And we simplify the right-hand side, which is 8k third. If it's a multiplication, you can actually distribute the exponent. And we divide both sides by 2. That gives us b third equals 4k third. Okay, apparently, this is even. Why? Because this is equal to 2 times 2k third, right? You probably don't need to show this, but this tells you 2 times the integer. That means it's even. Well, that tells us b third is even. Because b third is equal to that, if that is even, that means b third is even. And if b third is even, again, by number 3, so b is even, because that's what number 3 tells us. Number 3 says a is just a letter. I replace a with b. So if b third is even, then b is even, right? So that's just a different variable letter to represent the base. Okay, so that tells, again, that's why, because number 3, I proved it. Okay, so now we are looking at, let me highlight these two here. A is even, we know A is even, we know B is even. That's when we get a contradiction. Because when we picked the fraction, we made sure they don't have anything in common except 1. But now if they're both even, then AB has the greatest common factor. AB has a common common factor 2. Well, I'm out of space here. So contrary to this, contrary to GCDAB equals 1. Okay, when you get contradiction, that's when you can stop and say, okay, that's irrational. Okay. All right. Questions? All right. So let me go back to this example. And so this is also indirect proof. We want to prove A is even. Well, because I explained before in class, the one I did in class was if A squared is even, then A is even. Okay, so the proof is kind of similar. Again, why cannot we prove directly? Because if you know A cubed is even, you try to say, okay, let A cubed be 2k. And you try to get A, you will have to take cube root of both sides. Well, when you look at this expression, so A equals cube root of 2k. How can you tell whether this is even or not without knowing what k is? Cube root of anything, it could be, anything is possible. It could be even, could be odd, it could be irrational. So there's no way to tell whether this is even or not. So that's why direct proof does not work. Okay, so let's do indirect proof. Again, those 3 steps that I had here. So suppose the negation is true and try to find a contradiction. So we're gonna assume that suppose A is odd. Well, actually, we suppose A is not even, but the opposite of even is odd. Okay. But well, I'm gonna maybe after this I will try to give you a different example. So suppose A is odd, then if A is odd, then A must be 2k plus 1. I think almost everybody got this one right, so I'm going to move a little faster. And then you try to find a contradiction. What's the contradiction? Right now, there's no contradiction yet, but after I replace A with 2k plus 1 and take the third power, again, you got to do 3 copies, so you should get A third and 4k squared plus wait, hold on, that's that should be 3 times 3 times 2 4, that should be 12, sorry, times 12, and then 3 times 2 6 and plus 1. Okay, and notice that this cannot be even, right? So because we can factor 2 out of the first 3 terms, and there will be a leftover 1. That tells us clearly, because that's even. Well, when you add 1 to an even number, definitely it's going to be odd. So A third is odd. But what do we know about A third? That's the hypothesis. The problem tells us A third is even. So that's a contradiction. Contrary to the hypothesis that A third is even. Again, these 2 sentences, let me highlight them. A third is odd, which comes from my assumption, okay? But A third is even, that comes from hypothesis. Well, because the hypothesis is what what the problem tells us, it's true. So we only only possibility is that this must be false, that must be false. So A is even. Okay. All right. So you're gonna use this in the in number 4. But what if I give you something like this? If A third is divisible by 3, and ask you to prove A is divisible by 3. Again, you will still do indirect proof. Say, okay, suppose A is not divisible by 3. So you're going to negate that. not A, 3 doesn't go into A. Well, if 3 doesn't go into A, what kind of number is A? When you say A is not even, which means it has to be odd, right? Because it's even odd, only 2 cases. But if you have a number that is not multiple 3, what kind of number is it?
Even.
Not divisible by 3, it has to be even? I'll give you a number like 7. See, 7 is not divisible by 3, right? But it's not even. If it's not divisible by 3, what kind of number can it be? We have integers like, we have integers like 1, 2, let me just look at the positive ones, 6, 7, let me just list a few. So I know for sure A is not divisible, I'm assuming A is not divisible by 3, so it cannot be 3, cannot be 6, cannot be 9. But the left of the integers left could be 1 or 2 or 4 or 7, 8 or 10. The next one would be 10. So what kind of numbers are they? You cannot describe it in one way. Remember the first problem we did? What was the first problem? Look at the first problem. If a integer, all integers can be divided into 3 categories. Which 3 categories? Do you remember that?
3K, 3K plus 1, or 3K plus 2.
Yes, that's right. So if it's not if it's not divisible by 3, it just means it's not 3K. It could be, if it's not 3K, there are 2 possibilities. It's either 3K plus 1 or 3K plus 2. So you will have to do 2 cases and verify under each case, it's not going to be divisible by 3. I don't know if we did this in class or not, but I forgot if I did this in class or not. But does this make sense? Let me get rid of the page and rewrite it to erase this, not to confuse you with this when you look. Okay, so let me go back. Okay, so if they want us prove if 3 goes into a third, prove 3 goes into A. So first you suppose that 3 doesn't go into A. What conclusion follows? Previously, we assume A is, actually we should assume A is not even, but A is not even means A is odd, because any number is either even or odd. But when you have a number that's not a multiple 3, what does this mean? In English sentence means A is not a multiple 3. If A is not a multiple 3, we don't know anything about A. It could be even, could be odd. Like the list that I gave you, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. So if it's not a multiple 3, we can cross out 3, 6, 9, and those multiples of 3. But the numbers left, you can see that we have even ones, we have odd ones. So we cannot say A must be even or A must be odd. Okay, and like Madison said, integers. See, look, that's all the integers we have. If you cross out the multiples of 3, you could have those integers like 1, 4, 7, and 10. These are integers, multiples of 3 plus 1. But you also have like 2, 5, 8. And these are integers of multiples of 3 plus 2. So you will have to do 2 cases, find out A cubed equals what, and then you're going to show it's not divisible by 3. And for the second case, you also plug this into a third and show it's not, you cannot factor out of 3. Okay, so you will have 2 cases that you have to do. Okay, does it make sense? Questions? All right. So sometimes, like in this question, I have to do indirect proof, and then after I assume that the negation is true, I found out I still have to do 2 cases in order to find the contradiction. Okay, because if a number is not a multiple of 3, it could be multiple 3 plus 1, or could be multiple 3 plus 2. We don't know for sure whether it's even or not. Okay, now let's look at mathematical induction. We have 3 questions. I put the steps here, so 2 steps. First, you do basis step. I already did the basis step. Basis step is whatever they give you the smallest. Okay, kind of pay attention to that. I think one student did n equal to 1, but in this case, n equals 0. So you plug into the left-hand side. By the way, the left-hand side, we practice this in class. Again, if you have trouble with this, go back to watch the video for mathematical induction. If n equals 0, you don't have these anymore. You just have the first term. Okay. The right-hand side, yes, you just replace n with 0, and we find out that both sides are equal. Okay, because looks like from the grading, I don't think anybody had trouble with this. So I'm just gonna give you the answer here. Now, next we're gonna do the inductive step, because step 2 is usually the main part that we have to work on. So we're doing the inductive step. We always we need to prove that if the property is true for n equal to k, and we want to prove it is also true for n equal to k plus 1. So that's why you always start with this. This is what you start with. So I'm going to put this here. You start with this. So if you say I have trouble doing the step 2, then follow the format. You always write this down, and you always write down your goal. That's what you should end up with. The formula you proved the equation holds for n equal to k plus 1. Okay, so in order to see what the equation is, what is the equation for n equal to k? All you have to do is to replace n with k. So you're going to get 1 plus 2 plus 2 squared plus dot 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 plus 2 to the k equals 2 to the k plus 1 minus 1. Again, I think everybody did this one right, so I'm going to move a little faster and try to spend more time on the ones most had trouble with. Okay, so after you replace that, and again, you can write down the formula for n equal to k plus 1. You replace n with k plus 1. And usually, I've said this in class, I recommend that you write down the last 2 terms for the formula of n equal to k plus 1. Okay, so after we replace the n with k plus 1, there's another plus 1 that gives you k plus 1 plus 1, which is k plus 2. And after we replace n with k plus 2, the last term will be 2 to the k plus 1. And right before it should be 2 to the k. Now, after we compare them, so there are 2 ways to do. You can either add. In the class, what I did was all that is equal to this, right? So you can replace all that with this, and you can get that immediately. The other way you could do is to add 2 to the k plus 1 to both sides of the equation you have, and the left-hand side will immediately become the one we need. And look, after I write the left-hand side down, it matches with the left-hand side of the formula we need to prove. So this is our goal equation. And on the right-hand side, notice that 2k plus 1 plus 2k plus 1 minus 1. So I put these 2 together. And when you add these 2, it's just like x plus x. So think of 2 to the k plus 1 as x. What is x plus x? You get a 2x, right? But instead of having x, it's 2 to the k plus 1, okay? So 2 to the k plus 1 plus 2 to the k plus 1 should be equal to 2 times 2 to the k plus 1. It's like combining like terms. And that is by using the formula of exponent is 2 to the k plus 2. K plus 1 will be k to the k plus 2, and that matches the right-hand side. So you can stop right there. Okay, again, like I said, I think everybody got this one right. So I'm going to move a little faster. The third one, again, most of them got this one right too. To prove divisibility. So we are going to first plug 1 in here. So we end up with 2. 2 apparently is divisible by 2. Okay, so we don't have 2 sides. We're just having a statement saying 2 is divisible by 2. So that's the statement we want to prove. we can convert this to equation by using the definition of divisibility. Okay, so let's do the inductive step. So again, you assume, I'm sorry, not the equation, I should say statement. I just did the copy and paste, I forgot to change this. So we assume the statement holds for n equal to k, and we prove the statement holds for n equal to k plus 1. All right, so what is the statement for n equal to k? So we replace n with k. Then 3 to the k minus 1 is divisible by 2. And we use the definition to rewrite this. There exists an integer. Oh, I cannot use k anymore. I already have k. So let's use integer. I think a lot of students use a, so I'm going to use a. So exists an integer such that, now what does a number divisible by 2 mean? It means you can factor 2 out of the number, out of this expression. So you can write this as 2 times integer a. Okay, all right. We can also write down the statement if for n equal to k plus 1, which means 3 to the k plus 1 minus 1 is equal to 2 times some integer. Okay, is divisible by 2, or you can factor 2 out of there. There are two possible ways you can do. You can either, from this expression, you can add 1 to both sides. And that's going to give you 3 to the k equals 2a plus 1. That's one way. And then when you go back to this, continue from here. So you're going to get the left-hand side, 3 to the k plus 1, because I want to factor 2 out of here. But when I look at this, there's no 2 to factor out. And I'm going to use that, because notice 3 to the k plus 1 means 3 times 3 to the k. Again, we talked about this law of exponents. If you need more detail, go back to watch the class video. And notice that 3 to the k, that's equal to 2a plus 1. So we can replace that with 2a plus 1 and distribute that 3. After we combine the 3 and minus 3, we get a 2. Apparently, we are able to factor a 2 out of there. So that gives us what we need, right? So when you get here, you can stop. All that part is my thinking process. So you can say 2 divides 3 to the n minus 1, okay? All right, but there's another way I think I saw some student did was multiply 3 both sides. From here, you can do that. Okay, so from here, there's a different way. You can, when you get this, you can multiply both sides by 3. And you will get 3 to the k plus 1 minus 3 equals 6a. And we only need a minus 1 on the left-hand side. We don't need a minus 3, right? So you can add a 2 to both sides. And you get exactly the same thing, 6a plus 2, see 6a plus 2, okay? I did see a couple of students who did this way. That's usually a normal way. I guess, well, this is also a very common way, okay? But in the past, I usually teach this way. I taught this way before. And as you can see, if you watch the video, I post the extra video I post on Blackboard, that's the way I taught. But then I realized a lot of students had trouble with understanding this way, and they felt more comfortable with the substitution. So then I switched to this way, okay? But both way work, okay? Okay, now questions about this one? Okay, number 7. So for mathematical induction, we taught these 3 types. You can use mathematical induction to prove a equation like this, or to prove divisibility, or to prove an inequality. So in this case, it's inequality. First step, replace n with 1. And as you can see, after we replace n with 1, we got 2 on both sides. Of course, 2 equals 2, which means n will equal to the right-hand side. Now, the induction step. So we assume that inequality holds for n equal to k, and try to prove the inequality still holds for n equal to k plus 1. So first, we replace n with k. That's what we got. And the goal for our goal inequality, replace n with the k plus 1. Okay, so that's what we need to prove right here. But we already know 2k is smaller than or equal to 2 to the k. Okay, so we, I think a lot of did addition. You can also do substitution. So if you add 2 to both sides, how did we know we should add 2? Because after we distribute 2, that's going to give us 2k plus 2, right? So that's why we know, okay, we should add 2 to both sides because that's going to give us 2k plus 2 needed the left-hand side. On the right-hand side, unfortunately, we cannot get 2 to the k plus 1 directly, but notice that this is going to be smaller than or equal to 2 to the k plus 2 to the k, okay? Because 2 apparently is going to be smaller to an exponent of 2, right? This is 2 copies of 2 to the k because x plus x equals 2x, right? And by using the law of exponents, we get 2 to the k plus 1. So we proved that goal expression. If you look at the left, okay, the left-hand side, 2 to the k plus 2 is less than or equal to 2 to the k plus 1. And that's exactly what we need to prove. Okay, so when you get here, you can pretty much stop. Okay, questions? All right, now let's look at next. I think everybody got this one right. So because if the entire thing, including the curly brackets, see the entire thing is in another pair of curly brackets. So remember the most outside curly brackets represent a set, or in real life, it's like a group. If the whole thing is in the group and you say it's a member or belong to an element. But in the second case, we should use, you should still use belong to y because the entire thing is in a pair of curly brackets, right? So this curly brackets represent a set or a group. So let me highlight, oops, did the wrong thing. So if I highlight it, the entire thing, including curly brackets, is inside of another pair of curly brackets that's belong to. Entire thing, this time I don't have curly brackets, but the entire thing is in there, so it belongs to. But in this case, it's not the entire thing. Notice that too, I don't have curly brackets around it. Only the inside is the inside, okay? So notice that that's the left-hand side, 2 is inside a pair of curly brackets, and this 2 is also inside of curly brackets. So we are actually comparing two sets, and oops. And notice that this time we're going to use subset notation. So if a member is also a member of another, we say this set is contained in that. Okay. All right. So that's a bunch of definition we just have to memorize. Okay. So for this one, I guess the Venn diagram, I do kind of have, I think everybody got the answer right. Intersection, we look for the common one. So A and B, they both have 2 in common. So when you sketch the graph, notice, and this is A, B, they do have something in common. We put 2 in the common place, 1, 3, 4, and 5, 6. It's better for you to shade the final answer, because when you draw this, we don't know, is this the answer with this here? The answer is everything the answer. So it's usually you got to shade the area, shade the answer. So this is the answer. That's the intersection, which is 2. Okay. Now, similarly for the second one, and most students just drew A minus B. In fact, you should draw all of them. So this is still A, and this is still B. And we already know this part is the same as question 1. But where's C? C is not, notice that C has 7, 8, 9. Look, they don't have anything common. It's not going to overlap with A. It's not going to overlap with B. I noticed quite a few students had C intersecting with B like this way. Say that's C. Put a 7, 8, 9 there. You may say, well, I didn't put any number in the intersection, but if you draw 2 circles that they have overlap, they must have something in there. If they don't have anything in there, you're not going to draw that they are intersecting, overlapping. So it's going to be completely separated from A and B. Okay, so now I'm going to highlight the final answer. So what is the final answer? A minus B means I take A and delete 2 from A, because 2 is in B. We cannot. A minus B means something, anything in A but not in B, because 2 is in B. We cannot take that. Union C means together with C. So that's our C right here. So that shaded area is going to be the final answer. So that's, let me mark C here. So we write on the answer, what's in the shaded area? 1, 3, 4, 7, 8, 9. Okay, so this is how you should draw. If you don't have a highlighter, just shade it like this way. Oops. Shade here, and you shade here. Okay. Questions? Now let's look at. I guess this one is not. I don't see any big problems. So usually you can draw a interval to help, a number line to help you. So for example, A has from -1 to 2, so it's gonna go from here to here, and B is from 1 to 4. So apparently, what overlapping part is from 1 to 2. And notice that I do notice some students missed a little bit the sign, like equal sign, because 1 is included in there. So you must have an equal sign here. Okay, I'm going to go ahead and do part 4, because part 4 is related to part 1. It's asking for the complement of that. Complement just means anything not in here, not in the shaded numbers. So it's outside of, it's going to be left side of 1 and right side of 2, not including 1, not including 2. So that's going to be x less than 1 or x greater than 2. Okay, so similarly, you can do the complement of A. Complement just means anything not in A, right? So outside of A. By the way, please, when you write it, don't write. Well, actually, you can just go ahead and just switch it like this. You know, if you flip the sign, that would be the answer, right? Oh wait, actually, I'm sorry. You cannot do that. My bad. Okay. Actually, this is not correct. If you put like this, you actually indicated -1 is greater than or equal to 2, right? That's not possible. Because whenever you have 2 together, it means and, conjunction. So I do have to separate them into 2 of them. So it means x is on the left side of -1, or x is on the right side of 2. By the way, I have to have equal sign. If -1 is not in A, then it must be in the complement. But 2 is in A, so 2 cannot be in the complement. Okay. Now A union C, we can draw a number line. A is from -1 to 2, and C is from 4 to 5. And union means all of them. So it's going to be here, here. So we cannot really put them. Wait, hold on. Did I miss? What's C? Oh, C is. Oh, okay, yeah, that's right. So we have to just put 2 separate ones. So this or that. Okay. All right. And usually when you write down something, I guess we usually don't try to put something like that. We usually don't. Yeah, if you have to write something like this, you would separate it into 2. Okay. Okay, so that's any question about this one? The next one is going to be whoops. Again, most of them got this one right. So there are 2 problems similar to the one in the homework. So first you do product. I think everybody got this one right. So you just do the first complement element comes from A, second comes from B. So you have A1, A2. But don't forget you have to do power set. That P means power set. The power set means definition. I put it right here. It's the set of all subsets. So you need to list all the subsets of this. Usually when we list, again, you think of this as a point. A1 as point 1, A2 as point 2. So you may take no points at all. You may take one of the points. So you gotta have both parentheses and brackets. Parentheses represent this is a point or ordered pair. Curly brackets represent this is a set. Because we need to list all the subset. Subset is also set. So that's why we have to put curly brackets. So you may have 1 point, only point 1 or only point 2. You may have both points. Okay, so that you will have 1, 2, 3, 4 subsets. Okay, so that's the final answer. Okay, so now let's get to the difficult part, the proof problem. So this is something I had in the teaching when I was teaching the section 5.2. How do we got two types of question. You prove a set is a subset of another. This is what you should do. How do you prove two sets are equal? You got to do 2 steps. Step 1, show X is containing Y. Step 2, to show Y is containing X. So that's just the definition. Memorize that. But when you do type 2, look, type 2, you still have to prove X is containing Y, Y is containing X. That's exactly type 1. So pretty much for type 2 question, you have to do 2 type 1 questions. So this is like doing 2 type 1 problems, okay? Because you want to prove, type 1 tells you how to prove a set is containing another, okay? So as long as you know how to do type 1, you should be able to do type 2 because you just do type 1 twice, okay? That's what we have in our problem number 12. So we want to prove these 2 sets are equal. To make things easier, so you in case you forget how to prove 2 sets are equal, so that's like our X and that's our Y. You got to show X is containing Y, which means A union B is containing B. And you also have to show Y is containing X, which means B is containing A union B, okay? Again, if you want to know the detail, go back to watch the class video. Detail why we have to do 2 steps. So each step is like type 1 question. So here I gave you a format because I noticed a lot of students had trouble with the format. So I just copied the type 1 from here. I just copied the type 1 from here. But I want to give you a format to help you memorize. So what's the format of writing the proof of X is containing Y? This, the one in blue, that's the format. You always write down, you always start with let X be from X, which is the one contained in something. You always pick an element from this. So the first statement you write down in the proof is always going to be this. And what do you end up with? So this is what you start with. You're going to end up with this. You will say, so X is containing Y. And you just have to figure out how you're going to go from this statement to that statement. Okay, so remember that. So let's look at how we do this. That's like our X. That's like our Y. So remember, what do we start with? Remember what we start with? You don't have to, when you do the proof, you don't need to write this start with, but I'm going to write this here to help you, because I noticed a lot of students had trouble with this. So what do you start with in this case? Can anybody see that?
X is contained in A union B.
Yes, very good. Let X is actually not, we don't say contain, we say element. Okay, so a contain usually means this symbol. So let X be an element of A union B. Well, let X be a member, or X is in A union B. And you should end up with X is in Y, which is B here. You can say, so Y is in B, okay? Is this clear? At least you need to know what's the first sentence and what's the last sentence. You may have trouble to figure out the logical reasoning here, but that's always going to be the first sentence. So in this case, what's the first sentence? Let what? So what? So that's your X, that's your Y now. Anybody?
X equal B, or not equal, an element of.
X is in B, okay? Yes. What do you end up with, Madison?
That
X is in
X is in A, B.
A union B. Yes. Okay. See, it's always, they give you two, right? They always give you two, and you always start from the smaller one, the one being contained in the other. So you always have an x from here, and then show x is from in the other. So in this case, you x is from here to show x is in the other. Okay. So you at least need to know the format. Okay. And in the bonus, they actually ask you this. Start with the what, end with what, right? Okay. The bonus you can, I mean, if you haven't turned in, it's okay. Just try to turn in later, maybe by the end of this week, because I think that will help you with this problem. Okay, so now how do I figure this out? And you just look at the definition. What does this symbol mean? It means or. Then, following from that, x is going to be in A or in B. By the way, I think it was Marley, don't use the union symbol, use the word or. So we want to use sentences, words here. You can use symbol here, but for that, we don't really use union for statements. Okay, all right. So next, we have two cases. Case 1, x is in A. Because we don't know whether x is in A or x is in B. Possibly x could be in A, possibly x could be in B. Our goal is to show x is in B. As you can see, case 2, automatically true. Because case B, x says x is in B. That's why we need to prove. Okay, you can just say it's trivia or it's automatically true, whatever you want to say here. And if you want to say it again, so x is in B. Because but if x is in A, how do we prove x is in B? Take a look at the hypothesis, because they tell us A is contained in B. What does that mean? A contained in B. Graphically, that's what it means, A contained in B. And if A is contained in B, anything from A must be in B. If x is from A, that means x must be in B. Okay, we proved, we're done. Okay, so that's how you have to write. So we either case, I end up with what I need, x is in B. Okay. Now the second step, x is in B. Immediately you will know. We want to prove that, right? Immediately you get that. Again, I explained this in class. I used the example I used was the United States. Okay, so if you think of A as, say, Alabama, so A union B. Do we have any state that starts with B? Alabama. Do we have any? We don't, huh? Maybe I can change it to C, Colorado. Okay, so think about this. If I live in Alabama, then I belong to the union. So if suppose we have a union, which is the state of Alabama and the state of Colorado. Okay, if I live in Alabama, then I live in the union. I don't have to live in Colorado to be belong to the union. Okay, so if similarly, if x is in B, so x is in this state B, x doesn't have to be in A. I think a lot of confusion was some students try to prove x is in A. You don't have to prove x is in A. If you are in B, then you are in the union. Just like if I live in Colorado, then I live in the union. If I live in Ohio, then I live in the United States. I don't have to live in all the other 49 states in order to be in the union, right? So union just means all together. So this is automatically true. If x is in B, x must be in the union of B with any other thing. Okay, so let's just you can directly say, therefore x is in A union B. And why? Because it's the definition of union. Okay. All right, questions? So again, this is the confusing part. I think a lot of students thinking the intersection. If you want to prove x is in the intersection, you have to prove x is in A, x is also in B. But union doesn't need that. Union just, if you are in A, if you're in B, then you are in the union. If you're in A, you're in the union. You don't have to be in the other one. Okay, so that's something try to remember. Okay, so looks like some students had trouble with accounting problems. If you have trouble, make sure I posted some extra videos on Blackboard. So you, besides the class video, if you look at the grading of your practice exam, if you missed a lot of last few counting problems, and try to go over the examples again in those videos and try to do some more exercise in the textbook. Okay, so let's look at the first one. So it says we have a pin with 5 symbols, so which has 1, 2, 3, 4, 5. Cannot contain letters from A to M. Cannot contain N to M, which means from A to M we have 13 symbols. And that means we only have 13 left from N to Z. So we have 13 symbols available. Must end with a digit, which means the last place, this last spot, you cannot use a symbol. You cannot use a letter. I shouldn't say symbol, I should say letter. Okay, you cannot use any letter. You can only use the digits. So how many digits do we have available? 0 to 9, that's 10, right? So which means this over here, you only have 10 options for the last place. Now for the first 1, 2, 3, 4, 5, you have, because we want them to be all distinct, which means you have 13 options here. But after you use one letter, you cannot use it again. You only have 12 left, and you have 11 left and 10. So that's and you multiply all of them. Okay.
But
Yes.
so there's 13 letters available for the first one.
Mm-hmm.
But
Right.
it says, but couldn't you still have 9 digits?
Oh, yes, you're right. Okay, so this question is not very clear. I'm sorry. You could have plus. I was wrong. At medicine, you're right. So the second, the first few places should have plus. Plus 9. Okay, 23. So the first one should be 23. My bad. Okay, 22. Okay, so the reason they didn't say the first 4 cannot be digits. Okay, they could also be digits. But why do I only add a 9 instead of 10? Because we already used a digit for the last place. So last place is special. Make sure you meet the requirement of special place. So you pick a digit for this place. And then after you use this digit, you cannot use it again. So suppose you use the 0 for the last place, you cannot use 0 anymore. So you only have 9 digits left available, plus 13 letters. Together you have 23 available for the first place, and 22 for the second, and 21 and 20. Okay. You're allowed to use a calculator. I don't have my answer sheet, so use a calculator to find the answer. So we do need you to find the answer for that. Here I actually put all the rules here for your information. And the next one, so we have 5 seats, that one of them must be in the middle. So this one person, there's only one way to do that. And for the rest of 4 people, you could have put one here, and one here, and one here, and one there. I think the second one, probably everybody get this one right? So it's going to be 24. Okay, because once you use a person, you cannot use it again, use this person again, so you have only 3 or 2 and 1 left. Okay, the permutation, this one actually is permutation. It's also multiplication rule. 15.1, I don't know if anybody did this wrong. So apparently the order does not matter, because you just choose 6 people from 15 people. Who you call first, it really doesn't matter. That's 15 choose 6. There are different ways to write it. Many symbols for this. Wait, did I put an N here or 6 here? I forgot. So anyway, there are many ways to write the combination. When you work this out, there are also 2 ways to work it out. I think I remember one student made a mistake in the calculation. So the bottom has 6 numbers. The top should also have 6 numbers. Okay. So I think after you reduce, you should get 5,005. Okay. Now the final one, I have 1 minute left. So if I can, I guess I can quickly go over this. And like I said on Blackboard, I think under week 10 this week, I have extra videos there and to help you to do this type if you need more help. So this time we have special requirements. Out of 15 students, we have 7 women and 8 men. How many ways can we choose 6? such that the committee contains at least one man. Okay, at least one man. What we do is you could have one man, 7 women. You could have 2 men, 6 women, because I'm sorry, 1 man, 5 women, and 4, because you want to have a total of 6, right? So if you have 1 man plus 6 women, you have 6 people. 5 women, you have 6. So that's one possible way to do it, but this way is too tedious. At least 1 man, you could have 1 man, 2 men, 3 men, 4 men, and 5 men, and it's all 6 men. But so that's what we do is we are going to do the opposite. How about we found how many ways that such that committee contains no man? Contains no man, that means we have all the member we selected are all 6 women. And that's similar to question 1. So you have 15 students, choose 6 women. You are going to, I'm sorry, not 15. You have how many women? Because we want to choose 6 women, which means these 6 women have to come from 8 women we have. So it's going to be 8 choose 6. Okay. To do that, that's going to be equal to, let's do 2, 8, 7. So that should be equal to 28. Yeah. Okay. So I'll skip that, and you should be able to find out it's 28. And so there are 28 ways to choose 6 people without men at all. But from question 1 we just did, there are a total of 5,005 ways to choose 6 people. This 5,005 ways contains 1 man, 2 men, 3 men, 4 men, 5 men, 6 men, and no man. Okay, so if I subtract 28 from that, that gives me at least 1 man. Okay, so that's going to give us 4, 9, minus 28, 7, 7. Is it 7, 7? Okay, making mistakes. Okay, so the idea of the last question is, if I draw a circle to represent all the ways, 5,005 ways to, is that 5,005? Probably made a mistake on this one number. Does anybody have the answer, correct answer for this? What is that 15 choose? Does anybody have an answer for this? Let me reduce.
Is it? Oh.
Times 7. So it's gonna be a big number. I don't have my answer sheet. If you multiply this out, whatever that is, 35 times. Well, anyway, so this number, I don't know. You double check with your from your calculator, see what this number is. Might not be correct, but whatever that is. Right. What is that?
Yeah, that was right.
That was right? Okay. So anyway, so there are 5,005 ways. Out of all of these ways, you could have 0 men, 1 man, 2 men, and 3 men, and 4 men, and 6 men. That's all the possibilities. I already found out there are 20 ways for this little section right here. No man will be 28 ways. So if I do 5,005 minus 28, that's going to give me 1 man, 2 men, 3 men, 4 men, 5 men, and 6 men, right? So that's the easiest way to do this question. Okay, so that's the one where I'm looking for. But instead of doing all these 6 cases, that's just too many cases, and we can just do subtraction. Okay. All right. Sorry, I'm a little bit 3 minutes over time. And so, like I said, just come to the class next Tuesday, and we will take the exam just during the class time. And if you need more help with the practice exam or to study for the exam, you can send me an email and schedule a time to with me so I can help you with that. Okay. All right. So that would be all for today. Have a good weekend.
Thank you.
Thank you.